Today we're going to talk about numericals based on electrolytic conductance. Let's look at the first numerical. Having read this, let's write down what is given. Equivalent conductance at infinite dilution for ammonium chloride is given to be 129.8. For Na, which is given, ionic conductivity at infinite dilution for Na plus is given to be 50.1, and for Cl minus is 76.3. The specific conductance of 0.01 normal in which for ammonium hydroxide is given, and we have to find out the degree of dissociation of ammonium hydroxide at this concentration. Using Colruyt's law, we know that equivalent conductance of ammonium hydroxide at infinite dilution is given by ammonium chloride plus NaOH minus NaCl. Infinite dilution, equivalent conductance of NaCl is nothing but the ionic conductivity of Na plus and Cl minus, sum them up at infinite dilution. Substituting these values, we get 129.8 plus this minus 50.1 plus 76.3. So the equivalent conductance of ammonium hydroxide at infinite dilution is found to be 252.1. Equivalent conductance of ammonium hydroxide at this concentration is given by specific conductance multiplied by 1000 divided by concentration. So 9.6 into 10 raised to minus 5 into 1000 divided by 0.01, which is found to be 9.6. So degree of dissociation of ammonium hydroxide at 0.01 normal concentration is lambda divided by lambda naught. So 9.6 divided by 252.1, and the answer is 0.038. Second, the specific conductance of a saturated AgCl solution. AgCl solution, please keep this in mind that it is a sparingly soluble salt. So Ls of salt is given, Ls of solution is given, Ls of water is given, and equivalent conductance of the AgCl is given. We have to find out the solubility of AgCl in gram equivalent per liter. Let's write down the given. Specific conductance of saturated solution of AgCl is given. The water is given. Equivalent conductance of AgCl at infinite dilution is given, and we have to find out the solubility. For a sparingly soluble salt solution, the solubility is given by a specific conductance of salt, not the solution, into 1000 divided by equivalent conductance of the salt at infinite dilution. So specific conductance of salt can be determined by subtracting equivalent specific conductance of water from the specific conductance of saturated solution. So this is, the solution is 2.68 into 10 raised to minus 4 minus Ls of water is 8.6 into 10 raised to minus 5 into 1000 divided by 138.3, and the solubility is 132 into 10 raised to minus 3 gram equivalent per liter. Let's solve the next question. We have to find out the mean ionic activity of 0.5 molar sulfuric acid solution if the mean activity coefficient is given to be 0.131. The mean activity of an electrolyte, the formula is this, is C plus raised to x, C minus raised to y, 1 by V, F plus raised to x, F minus raised to y, 1 by V. Where C plus and C minus are the concentrations of the cation and anion, x and y are the number of cations and anions formed by one molecule of electrolyte, V is x plus y, and this entire term is nothing but mean activity coefficient. For sulfuric acid, H2SO4, we have it dissociates as 2H plus 1 sulfate. So x over here is 2, y is 1, so V is x plus y 3. C plus is 0.5 into 2, because when one molecule of sulfuric acid dissociates, it gives two ions of H plus. So when 0.5 moles of uh, sulfuric acid dissociates, you get 1 mole of H plus, and you get 0.5 mole of C minus. And the mean activity coefficient is given to be this. Then now substituting this value here, so mean ionic activity of the salt is electrolyte is given 1 square into 0.5 raised to 1 into 1 by raised to 1 by 3 into 0.131. The answer is 0.104. And the last numerical, equivalent conductivity of sodium nitrate is given as 105.2. The book does not give this. This is required for the solution. The equivalent conductivity of Na plus at infinite dilution should be this much. This should be given. This is not given in the book. So this data is required for the solution of this numerical. We have to calculate the transport number of sodium ion in the solution. So at infinite dilution, equivalent conductance of sodium nitrate is given to be 105.2, and the ionic conductance of Na plus at infinite dilution is given to be 50.11. We have to find out the transport number. Transport number of the cation is given by equivalent conductance of that ion divided by equivalent conductance of cation plus equivalent conductance of anion. So the lower part, the denominator, equivalent conductance of cation plus equivalent conductance of anion, is nothing but the equivalent conductance of the salt. So substituting this value, so it becomes 50.11 divided by 105.2. So the transport number of sodium ion in the solution is 0.476. It is not given, but we can also find out the uh, transport number of the anion, which would be 1 minus 0.476. So this will come to be 425. So the transport number of the anion is 0.524, and the transport number of the cation is 0.476. Thank you very much. That's all for today. See you next time.